This is work with a bunch of collaborators at the University of Illinois. The technical genius behind all of this is Amanda Benz. It's important to note, first off, the impact Blue Waters has had on the graduate development in both our group and Bill's group, Wen May's group. So I wanted to kind of highlight that from the forefront. The focus of this talk is on sparse matrix operations. These come up all over the place, and we're seeing new areas where the sparse matrix operations are the fundamental computational challenge throughout, whether it's matrix-matrix multiplication, contractions on large graphs and sparse matrices, inversions of different types of matrices. In this talk, I'm going to talk about a kernel called the SPMV, or sparse matrix vector multiplication. It sounds like a fairly benign operation, but it in fact can encompass a huge amount of computational cost during a simulation. One reason for that is if we think about solving AX equals B, I've written down the important lines in a conjugate gradient method here, and most iterative methods are going to follow this process. There's an all reduce, something that has collectives in it, and Paul Eller, a grad student at Illinois, and Bill Gropp are working on communication avoiding algorithms. But another dominant cost in this is the sparse matrix vector multiplication, whether it comes in the AP or in a preconditioner. And depending on the preconditioner, and I'm going to show you algebraic multigrid in a second, this can require 2 or 10 or 100 type numbers of sparse matrix vector multiplications. In total, maybe we're thinking of time stepping that's wrapped around these solves, we could easily be in the thousands for the number of SPMVs that are needed. So it's a major kernel, and it doesn't scale well, and it's not efficient. What I'm going to show you is using the machine layout on Blue Waters, we can significantly reduce communication. And using the consistent timings that Blue Waters offers, we've been able to develop accurate performance models. All right, so what does a sparse matrix vector multiply look like in parallel? On the left, I've given a data layout. So an input vector and the corresponding rows in the matrix and the left-hand side are all stored on some processor. In the right, I've noted where this data is sent, in this case in a 6 processor case. You can see the vector elements need to be sent to all of these processors, and that's what incurs the communication demands. If we compare the communication map for an all reduce or an inner product, here's a process ID versus process ID, and these are the communicating cores in that operation corresponding to a sparse matrix vector multiplication that uses point-to-point communication. Notice that there's a larger range of communication on the machine. On this right graph, I'm showing just an example from the matrix market where we use 500,000 rows per core and ramp it up to 50,000 rows per core, or non-zeros per core. And we can see that it starts to be almost completely communication cost. There's very little computing or flop cost in this. This aspect here makes modeling difficult. I'm going to show you some of our work on that. And one of the limitations is that we have a row-wise or very simple view in the reference implementation of a sparse matrix vector multiplication. So we're going to talk about some results with algebraic multigrid. In algebraic multigrid, we have effectively an operation that tries to whittle away at the error. And it does so by using a bunch of successively coarser or smaller types of matrices. And so you can think of algebraic multigrid as a whole bunch of sparse matrix vector multiplications, but using smaller and smaller matrices. And so if we look at the multigrid hierarchy, or the levels in multigrid, Here we have an A0 that has 26 non-zeros per row. And at the finest level, we have, or at the coarsest level, we have 66 non-zeros per row, but it's a much smaller matrix. What we're going to find is that this incurs quite a penalty in parallel. Let me show you an example of this. Here's a linear elasticity problem using MFEM, which is part of the Exascale project. This one's using 512 nodes on Blue Waters. And here I have the course levels in the AMG hierarchy. These should be cheaper, or they should be very cheap. And we can see they're actually more costly to perform a sparse matrix vector multiply. And that's just wrong. Here's a couple of observations. I'm going to show you 3 observations that led to this work. One is when we look at how we're spending our time in the multigrid hierarchy, here I have different levels, meaning different types of SPIMVs that I'm doing. Look at how many messages we're sending. So as the problems get smaller and smaller, we're sending more and more messages across the network. We're also sending larger messages across the network. So the first is that we have a large volume of messages that we have to deal with that are going across that network. The second thing is, here we have a test where we just increase the message size, and we increase the number of cores that are communicating on nodes. So I have a node over here and a node over here, and I increase the number of cores that are sending messages back and forth. And you can see the diminishing returns on this. So at low message sizes, we get more and more benefit with more and more cores communicating. But at larger message sizes, we're seeing a limit to that. And it has to do with the injection limit. Go ahead, Wenmei.
Are the communications still mostly because of the vectors?
Mostly because of the vectors.
Sending the vectors to each other?
Yeah, well, so this one's just a ping pong.
No, I'm talking about the previous.
Oh, yeah. Yeah, it's all vector communication. Yep. In matrix, you're sending matrix data. Yep. And so one of the things that we found here is that when we have more and more communicating cores, we're going to find diminishing returns on that. Go ahead.
So was the number of messages per multiply at that level, or how many iterations you had to do with that level?
Yeah, this is just one sparse matrix vector multiply at each level in the multigrid hierarchy, and the volume of messages blew up. That's a good question. So in this, we found when we have more and more cores communicating, that we have diminishing returns. We aren't hitting the peak rates that we'd like to. And this is some work that came out of some work with Bill Gropp and Phil Samphas. The third observation is that whether we're communicating on socket or on node or across the network with either a large number of communicating cores or fewer number of communicating cores, we get different types of transfer rates. So much smaller time if we're communicating on socket, a little bit more time if we're communicating on node, and then of course the longest time is when we're going onto the network. So it's those three observations that led to a different view of our sparse matrix vector multiply. So we took our same matrix, we didn't move anything, we just viewed it as a distribution across processors that are all on the same node. So in this example, node 0 has the first 2 processors, node 1 has the second 2 processors, node 3 and 2 has the last 2 processors. What this means then, if we think about who needs information on this block, it's everything on node. And so I can communicate all of my information, all of the vector information, just on node in that case. Same thing with the last N2 node here. I can communicate everything across all of those processors just on node. Let me give you a schematic of how this works. In standard communication, here I have node N and node M. I have a bunch of different processors that need to send their vector information to the SPIMV rows that are happening on core Q. And all of them are trying to communicate their vector data. Similarly, for core P, it's trying to send all of its data to all of the cores that need it. In a node-aware approach, we're going to do the following. We're first going to send to core P everything that needs to be done locally on node. Okay, so we can do that separately. Then we can take and aggregate everything on node before it goes off node. So all of these blue data entries in the vector need to go to core Q. We're first going to aggregate them on core P on a single node. We're going to send them all and then scatter them. And so at a high level, you can see that we've increased perhaps the number of times we're communicating, but we're doing that locally. And then in aggregate, we're probably reducing the number of times that we're communicating off node. So if you go back to the standard version, oops. Look at the number of times that you have to go off node in this case. And so there are lots of different variations to this too, whether you chop it up in different queue sizes, the way you aggregate, the number of times or the number of cores that are actually aggregating on a node, et cetera. But this is at a high level the kind of the base algorithm. So here's a picture of that. So we have, we aggregate, we do the intra-node communication, we scatter, and then we do the on-node stuff, or we do the on-node stuff beforehand. So here's some results on that same case study. Here's the maximum number of off-node messages. This goes down in our new approach. The number of on-node messages goes up. Remember, these are cheaper though. Second case, this is the message size. Message size goes down off node. It goes up off or on node. And in total, we have a dramatic reduction in total time. So in the left, this is beginning to look like something that we'd want out of a multigrid cycle. It's much cheaper. Even in the strong scaling case, where we're keeping a fixed problem size, there's large benefits to this node or topology where distribution in the SPIMV. I'm going to highlight two things out of our cost analysis on Blue Waters. Blue Waters provided a unique setting for this for two reasons, in two aspects. We had very consistent timings, and also we had a very predictable layout for our computations. If we tried to model our sparse matrix cost, one of the things that was building up in our computations was the queue search time in MPI. So before things were sent, there's a large queue of information we have to search through that list. We ended up being able to identify a quadratic cost to this MPI queue time. In addition, there's also an issue with network contention. One of the things that we were able to do on Blue Waters that we haven't been able to do on other machines is set up a modeling test where we line up a bunch of nodes on the network. We do a ping pong across all of those nodes and measure how much contention we're getting in that single run. And that's been a unique element of running stuff on Blue Waters, and it's identified a hop model for gauging network contention. Here's the total modeling time. So we can have these measured costs in the AMG hierarchy, and you can see that just using a bandwidth model that we typically use doesn't really identify the total cost. We've been able to identify queue search time and some contention time in the total cost of the SPIMV. So here's a summary of what we did. We've identified a kind of a drop-in replacement for a range of sparse matrix operations: sparse matrix vector, matrix, assembly operations, maximal independent set operations. Blue Waters has been instrumental in both testing this at scale, but allowing for reproducible outcomes, accurate performance analysis. It also led to standing up two rather large code bases The work that I reported here is part of the Raptor code base, which is a unstructured parallel algebraic multigrid code. And then the Cedar project, where we're doing some structured redistribution of data based on accurate performance models.